Two students, and welcome to the last lesson of Chapter 4, where we're going to take a look at Section 4.8 dealing with what are called complex numbers. This is a new set of numbers that we have not dealt with before. If you remember back in Chapter 1, we talked about all the different sets of numbers, the real numbers, the irrational, all those kind of things, rational numbers, integers. Well, we never talked about complex numbers or imaginary numbers. Because at the time you've never dealt with those. Today is going to be your first introduction. Okay, so I'm going to start off with this warm-up and take a look. If we're going to go through and solve this equation, the idea, let's start on the left-hand side here. If I wanted to solve this equation for x, I need to get the x squared by itself. So I'm going to subtract the 16 over, which means we would get x squared equal to negative 16. And at this point in the past, you would have probably said, well, there's no number that I can square to get a negative answer. Okay? And that is a true statement up until today. There is no answer that you could get, no real answer. But now, when we take the square root of both sides in an equation, the square root will cancel out the squared, leaving you with x. Okay? Because we're taking the square root in an equation, we always have a plus or minus. And the square root of 16 is 4, but because it was negative, we can now attach an I standing for imaginary. Okay, so there is an actual solution. It's just not a real solution. And as we work our way through this, we'll talk about that as we move through the lesson. Some jobs that actually use imaginary numbers and so on and so forth. So let's now take a look at this second warm-up problem. Again, I'm going to try to solve for x, so the first thing I need to do is get that term by itself. So I'm going to subtract the 31 over, giving me x minus 3 quantity squared equal to negative 1. And again, we're in that same boat where we're squaring something, but it equals a negative. Okay? Well, I can still take the square root of both sides to get rid of the square. That will leave me with x minus 3 equal to plus or minus, the square root of 1 is 1. Because it's negative, we can attach an I to it for imaginary. Okay, so we get plus or minus 1i. Only thing left to do is add the 3 over. And I end up with 3 plus or minus, I'm just going to put I rather than 1i. And so once again, I have solutions. They're just not real solutions is the idea. And we'll talk some more about that, like I said. Okay? So objective for today is to be able to use complex numbers, understand what they are, and then be able to do different operations with them. Okay? So first off, here's your definition. An imaginary unit is defined as the variable I. Okay? The number I, if you will, just like there's a number for pi, there's a number, there's another number later in the class we'll talk about that's the number e, which we'll get into, but I is defined as the square root of negative 1. Okay? So if you see the square root of any negative number, you know you're going to have an I in your answer, standing for imaginary. Okay? So therefore, what is I squared? This is going to come into play as we take a look at this. So if you think about it, if you just take this definition right here, and let's say that I square both sides, I need to get to I squared. That would mean I squared then equals, well, when we square a square root, they cancel each other out. That means I squared equals negative 1. Okay? So keep that in mind. We're going to use that later in this lesson. The fact that I squared equals negative 1. That will come back and help us simplify some things later on. So that's your definition of an imaginary number. And so you might be thinking, where the heck do we use these imaginary numbers in real life? Well, one of the main places is in electrical engineering. There's a lot of stuff with electrical things that deal with imaginary units. Another spot would be sometimes software engineers where they're writing a program. Sometimes when you write really complicated programs, you may end up having to go through and use imaginary numbers in order to kind of check your program and make sure that things are working. So there's a couple of places. There's not a ton of places in real life that use imaginary numbers, but there are some that you have to deal with. Okay, so that's why we talk about it in this class. So if we go back to the warm-up, okay, we kind of already did this. I don't know that I'm going to go through and actually do this because I already talked about the idea of adding the I in, okay? But let me add in some other examples here. If now we're going through and we're trying to simplify square roots. So if we take a look, not too long ago when we were talking about the quadratic formula, we talked about simplifying square roots. So what I'm going to take a look at is, if I go through and factor this, and I'm looking for a factor, remember the biggest perfect square, that's a factor. So I'm going to go through and put this one as the square root of negative 25 times the square root of 2. Which then, the square root of negative 25 is 5i, okay, the I because it's a negative square root, and there's nothing else that I can do with the square root of 2, so therefore there's my simplified version. Again, not a real answer, but it is still a solution to this problem. 5i times the square root of 2. Same idea over here with the square root of negative 288. If you're looking for this biggest perfect square that's a factor, I'm going to factor this into the negative 144 times the square root of 2. Square root of 144 is 12. Because it's the square root of a negative, I'm going to attach an I to it. And again, the square root of 2, there's nothing else that I can do with. So there is your now simplified version of square roots of negatives. Okay, so we have that. So let's say that we encounter this in the quadratic formula. If we go back to that, that's why we did the simplifying of square roots. So if you take this example, x squared minus 7x plus 14, notice it does equal 0, so I can use the quadratic formula. If I take care of the discriminant first, I plug in my b squared minus 4ac. I end up with 49. There's only one negative sign here between these three numbers, so I end up with a minus 56. Which means negative 7 now is my discriminant. So at this point in the past, we said, all right, you can stop there and there's no real number, there are no x-intercepts, there's no real number x-intercepts. And that was a true statement, and there still are not, there are no real numbers for x-intercepts, but it doesn't mean that we cannot find the imaginary answers, okay, and we'll talk about that. So now if we go through and we finish up this problem here, we've got x equals opposite of b, so b is negative 7, so therefore positive 7, plus or minus the square root of our discriminant, which in this case is negative 7, we just found that, all over 2 times a, which in this case would be 2. And so now we can simplify this at least a little bit by going through and x equals 7 plus or minus, I can, because it's the square root of a negative, I'm going to bring the I out front. The square root of 7, there's nothing I can do with. I can't simplify that at all like we did on the previous slide, so I'm going to leave that alone. All over 2, and that's as far as we can go. So those are the imaginary solutions to the quadratic formula. Again, it does still mean, though, that there are no real solutions, which means there are no real x-intercepts on the graph. Okay? So if this happens in your homework, and it will, okay, make sure that you still find the imaginary solutions even if you can't put them on a graph. Okay? So speaking of a graph, let's take a look and see what this looks like. So how does this actually apply to graphing? What does that mean? What does that actually look like? So if we take a look, let's go through and actually find all of this information and see what we have. So for the vertex, let's start with that. Since we're in standard form, that means the x-coordinate is going to be the opposite of b over 2a. So opposite of b is negative 2. 2 times a is positive 2, which means my x-coordinate of my vertex is negative 1. Okay. If I then take that and plug it back in to my problem to find the y-coordinate, that means negative 1 squared plus 2 times negative 1 plus 4 gives me a corresponding y-coordinate of my vertex as a positive 3. Right away then, that means my axis of symmetry is x equals negative 1. It's going to go right through the vertex. My y-intercept, remember, if I were to plug in 0 for x, I would get my c value, which in this case is going to be 4 for y. So that's my y-intercept. The x-intercepts in this case, if you went through and you tried to find the x-intercepts, and you went back to factoring, you would not be able to factor it, which means we need to go to the quadratic formula. So for now, I'm going to skip that part, and we'll do that down below, and I'll come back up to that. Domain in this case, I did not put the a value in there. Let me do that first. I'm going to kind of skip that. So the a value in this problem is a positive 1, which tells me that this is opening up. Okay, so I know that this parabola opens up because I've got a positive a value. So that means my domain then, we've talked about before, domain and range. You can square any number, which means your domain is all real numbers. Or again, you could write it as interval notation, meaning anything from negative infinity to positive infinity, and everything in between. So you can plug anything in you want. The range, however, because this is opening up, that means my vertex is a minimum. So the range is going to be y is greater than or equal to the vertex, okay, the y coordinate of the vertex. That means your low point is at 3. Or again, if you write that in interval notation, you would have a bracket, meaning that we are including 3, and then it's going up to positive infinity from there. From 3 to infinity are the y values. Okay? So now let's go back to our x-intercepts and actually find those values and plug those in and see what we get. As usual, I'm going to start with the discriminant. Okay, so b squared minus 4ac. So b is positive, I'll put this here, b is positive 2, so 2 squared minus 4 times my a value, which is 1, times my c value, which was 4. Okay. 2 squared is 4. If you notice again, I only have one negative out of these three numbers, so this is going to stay as a minus sign. I multiply those together, I get 16, which means my discriminant is negative 12. So we do know that I'm going to get imaginary x-intercepts, meaning there are no real x-intercepts, and we'll show you what that looks like in a second. So now if we actually find those, let's plug those in. X equals opposite of b, which is negative 2, plus or minus the square root of negative 12, our discriminant, all over 2 times a, which in this case would be 2. If we keep going then, x equals negative 2 plus or minus, we have to now see if we can simplify this square root of negative 12. And I'm going to do that off to the side because we can. Square root of negative 12, if I go through and factor that, I'm going to factor it to the square root of negative 4 times the square root of positive 3. Square root of negative 4 is 2i. Square root of 3, there's nothing that I can do with. So there is your simplified version of the square root of negative 12, which means that I can plug in. So I have 2i square root of 3. I can substitute that in over 2. And now the last thing that you can take a look at here is that I've got a 2 in each one of these spots, so I can divide everything by 2 to simplify this. So my final answer here would be negative 1 plus or minus I times the square root of 3. There are your x-intercepts right there. Okay? Negative 1 plus I square root of 3. And that's what I'm going to put up here. Negative 1 plus or minus I times the square root of 3. So you can still find your x-intercepts. You're just not going to see them on the graph. And let's take a look at that now. So if I go through and actually graph this, vertex is at negative 1, 3. There's that point. A value is 1, so I can go up 1 over 1 from the vertex in both directions, but only for the first set of points. It also matches up with my y-intercept then. Okay, there's your 0, 4 that we had. And in this case, we said this is opening up, which makes sense. And so there is at least kind of a rough sketch of what your parabola should look like. So notice there are no x-intercepts in this case. It does not cross the x-axis, which is why those x-intercepts are imaginary. Okay? There again, there is still some answer that we can come up with. You just don't see it on the actual graph. Okay? The other option is this could have opened down and been entirely below the x-axis as well. So just a heads up what that looks like. when we've got imaginary x-intercepts. Okay, so let's go through and kind of take a look at where this fits in. So if you think back to chapter 1 and the real numbers, if you notice, there was no place for the items that had an I in them. These were all, we use this exact same thing, and that is because the imaginary ones would kind of be over here all by themselves. Okay, because if they're imaginary, that means they are not real, so they are none of these different problems. Okay? So if we take a look then, here's kind of your definition of a complex number. If we take a look, it is defined in terms of either I plus or minus bi. Okay, I plus bi, where a is the real part and the bi is the imaginary part. So if you were going to go through and write these as real numbers, to give you an example, you can write a real number as a complex number. For example, the number 3, if you wanted to. We could write that as a complex number. We would just write it as 3 plus 0i, okay? Which is why we just write it as 3. We don't ever include the imaginary portion because it's 0. I could go -4 plus 0i. That would also be how I would write -4 in complex number form. However, your final answers are going to be in this I plus bi form when we do have imaginary numbers. So in that case, you might end up with something like 3 plus 2i, or -4 plus 7i, or something along those lines. Okay, so just in general, just wanted to give you kind of the definition of, or the form that you would write complex numbers. You start with the real number, and then you add or subtract the imaginary portion to it. So the last couple things we need to do then is just some basic operations with these complex numbers. So whenever you add or subtract complex numbers, those i's act just like regular variables, just like x's or y's, and you add them just like you would in combining like terms. Okay, so for example here, in example number 1, if we take a look, if I wanted to add these two complex numbers together, I just add the real part plus the real part, imaginary plus imaginary. We're just combining like terms is all we're doing. So 3 plus 1 would give me 4. -2i plus a positive I would give me a -1i. And there's your final answer. Okay. Just combine your like terms is all you're doing. Same idea down here in example number 2. The only difference is now I'm subtracting two complex numbers. So subtract the real parts, subtract the imaginary parts. Again, still combining like terms. 5 minus 3 gives me 2. I minus a -8i, because I'm subtracting a negative, it means I'm going to add. So we end up with plus 9i. And there's your final answer there. Okay. And we could go even further with this. I don't even think I'm going to bother. Okay, but the idea is just combine like terms just like you normally would with x's or y's or anything. Okay? Nothing different. You just now have an I. When you are multiplying complex numbers, just like multiplying with variables, except for one exception, that this is where that I squared equals -1 is going to come back into play, which we'll talk about. Okay, so you never want to leave I with a power greater than 1. So you don't want any I squareds, you don't want any I cubes, any of that kind of stuff. You want to take care of those types of things. So, so let's take a look here if we were going to go through and multiply. Let me do this one first. Okay, so in this case, we're just going through and we're just distributing a -4i. So if I distribute that, we would end up with a -12i, and then we have a -28i squared. But we don't want to leave things with I squareds. It's okay to leave them as an I, but we don't want I squareds, I cubes, any of those. So here's where you got to remember. I squared equals -1, which means we're going to make a substitution at this point. So instead of the I squared, I'm going to take that out, and I'm going to substitute in a -1 in its place, okay, because that's what I squared equals. So now I have a -12i. -28 times a -1, this turns into a plus 28, okay? And there is your complex number. Or if you wanted to rewrite it so that the real number comes first, you could write this as 28 minus 12i. Now it's more in that complex number form. Either one of those is fine, though. Okay. If we take a look here where I'm multiplying binomials, Remember, when we multiply binomials, we're FOILing, if you will. So we're going to go through and just distribute. Okay? So 5 times 1 gives me 5. 5 times negative 2i is negative 10i. Then I move over and distribute this negative I, meaning I have a minus 1i, and then I end up with a plus 2i squared. And now we simplify. So that's all just straight algebra. Now we simplify this. I end up with 5. I can go through and combine some like terms. I've got a negative 10i and a negative I. If I put those together, I get a negative 11i plus 2i squared. And finally, because this is I squared, remember that's negative 1, so what's really going to happen is we have 5 minus 11i. That's going to turn this into a negative 2, which now I can go through and combine those two like terms. So I end up with 5 minus 2 is 3 minus 11i. Okay? So the only thing you have to do when multiplying is when you get to the I squareds, you have to substitute in negative 1 and then simplify a little bit further. Okay? General rule, remember, of math is always simplify if you can. And in this case, we can simplify I squareds. That's why we're doing it. All right, the only other thing that, I think that's it, actually, now that I think about it. So, practice to learn is the 4-8 worksheet. Hopefully this made some sense. I know it's a little bit confusing, just this whole idea of imaginary numbers. This is just your introduction to it and your introduction to working with it. So do the best you can on your 4-8 worksheet and come to class with any questions that you may have. Okay? Good luck, and we'll see you in class.